So our second speaker is Fractional. He's going to talk about the geometric response of quantum Hall states to anisotropy.
Thanks. Thanks, Bert, for organizing this. Thank you all for coming. It's great to have you. It's great to be able to present in spite of the March meeting being cancelled. My name is Akshay Krishna, and my talk is about the geometric response of fractional quantum Hall states to anisotropy. This is based on work I did at Princeton with fellow graduate students Matteo and Fan, and my advisor, Professor Ravi Bhatt, who's in the audience. Our work was published in PhysRev B a few months ago. You can check it out. All right. So before I get to the main discussion, here's some introduction, which very conveniently for me, going after some file is a little easy. This is about the quantum Hall effect. And the quantum Hall Hamiltonian for a non-interacting two-dimensional electron gas in a perpendicular magnetic field just consists of a kinetic energy term, but in the lowest Landau level, the dispersion E of k is absent, and each Landau level is macroscopically degenerate with a sharp delta function like density of states like this. So this makes it an exciting playground for correlated electron physics, because the many-body ground state is set by the interaction term, this term in purple, which would be Coulomb interactions typically. And depending on the type of the interaction and the position of the Fermi level within this band, we obtain many different kinds of phases. So there is the celebrated fractional quantum Hall phase, obtained at various kinds of fillings. It's a gap phase, and it's the focus of this talk. There are also gapless phases that are sort of metallic-like, other exotic phases that have broken symmetries and so on that I will not talk about. All right. So as it stands in its simplest formulation, this problem is rotationally symmetric, which makes it easy for theorists. So we often take it for granted. This is the Hamiltonian. But in real materials, such as for instance gallium arsenide or silicon, the electron might see the effects of an anisotropic effective mass, in which case the kinetic energy splits into two terms, depending on mx and my. Or the material may have a dielectric constant that's not a scalar. So now the interaction term has this tensorial representation. It's more complicated. It's possible to rotate and rescale the coordinates to get rid of one of these anisotropies, but not both. So we can assume that this interaction anisotropy is absent, and we only have this remnant mass anisotropy to deal with. Now the question is, given that the Hamiltonian has this anisotropy quantified by the square root of the ratio of the effective masses, we call it alpha, to what extent does the many-body ground state know about this Hamiltonian anisotropy? So that is alpha QH. So the focus of this talk is to sort of compute the linear response for different kinds of interactions. So we make the Hamiltonian a little bit anisotropic, which means we change alpha to be a small number, a little away from 1 plus something, and we measure what the ground state wave function feels. Because alpha equals 1 is the symmetric point, we work in logs of these quantities. So log alpha is gamma, which is a small number, and log alpha of the ground state is sigma, and expanding to first order, we get sigma is some coefficient times gamma. This coefficient C1 is something between 0 and 1, and it's what we're trying to find out. And the reason this talk is titled the geometric response is because effectively the wave function has a metric degree of freedom which you can optimize over, which allows it to respond in this way. So we're trying to find out what C1 is. All right, this is a complicated interacting Hamiltonian. How do we solve it? We use a numerical method called IDMRG, where first we put the two-dimensional system on an infinite cylinder. And the advantage of this is that in the Landau gauge, the basis wave functions have this form, up to normalization and a complex space, which almost looks like quasi-one-dimensional. These are Gaussians peaked at a certain value of x. And now we have a sort of quasi-1D Hamiltonian, and we can use a technique that works well in 1D for interacting Hamiltonians, which is IDMRG. It just stands for infinite density matrix renormalization group. What that means is just it's a variational ansatz over translationally invariant states with limited entanglement. So we exploit the translational invariance of system and write what is called a matrix product states ansatz, which looks like this. This is essentially like a spin wave function. There is a product over all orbitals, that the orbitals are given by these basis functions. These orbitals are localized at some sites, and they can either be occupied or empty, so or mapping into spin language, either spin up or spin down. Each of those configurations has a certain weight, and we sum over all configurations. By letting this M be a matrix and not a product, we can capture a state that is not a trivial product state, it actually has some entanglement. And by minimizing the energy over the parameters of this matrix, we end up with a suitable approximation to the ground state. And it turns out within very reasonable values of these numerical parameters, Ly, which is the circumference of the cylinder, and chi, which is the bond dimension, which is the size of the matrices we use, we get good convergence. Alright, so I told you about the anisotropy of the Hamiltonian, but what does it mean for the wave function to be anisotropic? To quantify the wave function's anisotropy, we compute the guiding center structure factor, which is related to the Fourier transform of the density operator. And this quantity is a quartic in the momentum kx. But what's important is that the prefactor here contains the desired linear response coefficient C1 that we're looking for. This is for gap states. Just to mention, in gapless states such as the CFL, which are not the focus of this talk, we can actually probe the composite Fermi surface, which has a different shape than the bare Fermi surface, and that allows us to calculate the response to anisotropy. Alright, so now it's time for results. First, we look at gapped fractional quantum Hall pairing states, such as the ubiquitous nu equals 1/3 state and the nu equals 1/5 state, and we consider power law interactions of the form 1 over r to the p with different kinds of p. So p equals 1 is Coulomb, and we can increase p and make it effectively a shorter range interaction. The first thing we notice is that as p increases, more anisotropy is transferred to the ground state, or C1 goes up. And that kind of makes sense because as the interaction becomes shorter range, it becomes less influential at tempering the effects of an anisotropic bandmass. The second thing we notice is that the nu equals 1/3 state, which is the blue line, responds more strongly to anisotropy. This is again expected because the state at lower filling, which is 1/5, in some sense binds to more magnetic fluxes, and since the interaction is isotropic, this washes away the effects of asymmetry in the non-interacting part of the Hamiltonian. But the most interesting thing in this figure, according to me, is the fact that there is a kink here, and kinks are always interesting in physics. So it seems like, modulo numerical accuracy, that above a power law of 1 over r to the 4, the anisotropy transfer is complete in the sense that the interaction does not do anything to dampen the effects of the bandmass anisotropy. And that is quite interesting. So why exactly does this kink happen? To understand this, we need to understand what exactly the electron gas is trying to do in order to minimize its energy. So the ground state energy can be written as this expression, where Ne is the number of electrons, and it's a sum over these kinds of terms, which have two parts. The first is Vn, which is the Haldane pseudopotential, which is just a representation of the interaction potential in a basis. You can think of it like a Fourier basis. And An, which is given a wave function, what is the probability that two electrons have a relative angular momentum n times h bar. So the Laughlin wave function is a special wave function that at a given filling has An equal to 0 for all n less than m, where nu equals 1 over m is the filling. And it's a very good approximation to the exact ground state because typically the ANs are decreasing. So A1 is less than A3 is less than A5. And so, I'm sorry, typically the B are decreasing for any reasonable potential. So V1 is less than V3 is less than V5. And if you set the small h to 0, you can minimize the ground state energy. The key is that for non-Coulombic interactions, so the form 1 over R to the P, the pseudo-potential goes to infinity when P is greater than 2 times n plus 1. So what this means is that combined with the fact that these terms go to infinity and these terms go to 0, the only way that the ground state energy can be some reasonable non-infinite number is for the Laughlin wave function to become the exact ground state above a certain interaction power law. So when this happens, the interaction effectively becomes like a contact interaction, and the ground state completely inherits the asymmetry of the Hamiltonian, because the Laughlin wave function can be written directly in terms of the stretch and rescale coordinates. So that's what's going on. That's what causes the kink. More results. We also did the so-called daughter state. So for example, nu equals 2/5, 3/7, and so on are daughter states of nu equals 1/3. And we find that with the numerical accuracy, they respond exactly the same as their parent states. And this is as expected, because the ground state of the ground state of wave function of a daughter state can be written in terms of Laughlin wave functions for quasi-particles. We also did bosonic states, and we see similar things as in the fermionic states, increasing response as P increases, the higher filling fractions responding more strongly than lower filling fractions, and the daughter states responding the same as the parent states. The explanation is the same as that in terms of the Laughlin wave function and ordinate pseudo-potentials. We also went beyond elliptical anisotropy, which is to say that you can distort the bare Fermi surface from being elliptical to having these fourfold distortions. And in the interest of time, I will just run through these results. What's interesting is that these results on the left are from the previous slides. On the right, we see that the linear response to fourfold symmetric distortions is much less than for twofold symmetric distortions, but comparable between the two fillings 1/3 and 1/5. And our hand-waving explanation is that the Laughlin state at nu equals 1 over m naturally admits Cm-1 distortions. So 1/5 state naturally admits C4 distortions and is able to react and have a sort of comparable response to anisotropy. All right. So that brings me to the conclusions. And what we basically found is that there are many factors that influence the extent of anisotropy transfer, such as the ground state phase, the filling, particle statistics, whether it's fermionic or bosonic, and the interaction type. We see a kink because of this effective contact-like interaction above a certain power law. And you might ask, why are we doing all this? Surely, electrons are fermionic, they have Coulomb interactions. But the point is that we are entering an era where quantum Hall is being studied in, non-gallium arsenide materials. So, light, photons, dipolar spins, which interact by dipole 1 over R cube interactions. So it's important to see what happens in these cases, and our work provides guidance on that. With that, thank you to my collaborators, my advisor, funding agency, and to you all. You can read our paper here.